What if we map out a representation? What if we do something different? All right, I want you to think out of the box now. Ready? Instead of just dealing with a sign and putting a bit for a sign, let's get that out of our head. Let's say that a negative 70 is not the same thing as a 70. It's not. Right? They're on each end of the spectrum. Negative 70 means I don't have 70 things. Positive 70 says I do have 70 things, maybe clocks or whatever that we were dealing with before. Negative 70 says I'm short 70 clocks. Plus 70 says I have 70 clocks. They're two separate numbers. So what if we forget about the sign? What if we do a different mapping? We think in mappings, right? How do you distribute your data? I want you to think of it that way. What if we could take the total range of bits that we have available, and what if we split them in half? And we say that one half is for positive and the other half is for negative. Think about your number line if you go all the way back to when you were back in grammar school. Think about that number line. You had a 0, and on one half of the line were the positive numbers, and the other half of the line were negative numbers. Wouldn't that kind of make sense to you then that we would take a binary range of numbers, just like on that number line, and we'd split it at a 0. And we'd say that, okay, this range of numbers is for positive, and this range of numbers is for negative. That has some merit to it. Let's try that instead. And let's just see what happens, okay? This is going to be a couple of step process to get there, but now we're on the right track. I'm just going to give you that hint. We're on the right track. All right, so let's take our 6 again. This time, it's not a sign bit, it's a 0. So there are no 8s in there. So instead, I've got 4 plus 2, that's 6. Now, what I'm going to do is I'm going to say that with a 4-bit system, my total number range is what? I can go 0, 0, 0, 0, 2, all ones. And those all ones are equal to what? Come on. Think about that. You should know what a 1, 1, 1, 1 in binary is by now. You should also know what it is in hex. In hex, it's a F. In decimal, it's a 15. 8 plus 4 plus 2 plus 1 is 15. Okay. Let's split that in half. So let's say 0, 0, 0, 0, 2, 0, 1, 1, 1. Let's say that our half numbers is 0 to 7, right? All right, so we've got a range of 15 there. So we're going to say 0 to 7 are for the pluses, and negative 7 to 0 is for our negative side. Yeah, that makes sense, right? So if I have numbers from 0 to 7, that's assumed to be positive. And the next half of my number range would be a negative. So therefore, that would be starting at 1, 0, 0, 0. That's an 8 up to the 15 decimal, which is 1, 1, 1, 1. Okay, and that would be representing negative 7 to 0. So my numbers are ordered by smallest in the range. Did you see that? All right, let's lay this out. All right, this doesn't look any different than what we just talked about. So we went from a decimal 0 to 7, and then we put in the 4-bit binary for what each one of those are. Now let's look at the negative side of that and watch how it's populating. So if I start down there at 7, what did I say? A 7, if it's negative, would be a 1, 0, 0, 0. And then the pattern would just continue up until the 15, right? Up at 0. Well, what's my problem here? Yeah, exactly. I have 2 zeros still. And we're going to deal with that problem in a minute because the rest of this has validity to it. So ignore the 00 just for right now, and let's deal with everything else. I want you to look at this and I want you to see a pattern. What do you see? Ignore the double zero, but what do you see? Can you see a pattern? Now stretch yourself a minute. Take a look at, well, let's just look at the zero. That one is so obvious. That pattern should be jumping out at you. On the positive side, it's a 0, 0, 0, 0. On the negative side, it's a 1, 1, 1, 1. What is the pattern? What do they have in common? One is all zeros and one is all ones. The negative ones are inverted, right? They're flipped. Do you see that? Look at that pattern as you go all the way down. A 0 on a positive becomes a 1 on the negative, and it's flipped all the way down. So we invert the positive bit pattern for negative numbers. Oh, that's kind of cool. That's called ones complement. I want you to take a minute, and I want you to look at this chart and think about this a little bit. Think about what we just did here. We split our number range in half. And when we did that and we lined it up from the numbers being ordered from smallest in the range up to the biggest on both sides, positive and negative, when we did that, we ended up just inverting the positive bit pattern. Huh, cool. Let's see how this works. All right, flipping the bits. So here is for a 2 in decimal. Ready? So that's what it looks like. That's a 0, 0, 1, 0. Now let's flip the bits for negative. Watch this. That's a 1, 1, 0, 1. Now think about that. You see how easy that was? And that's just a subset of what we did. So for you to remember one's complement, all that you have to remember is to flip the bits. The breaking it down in that we split the range, that's an important concept too. I want you to think about being able to split ranges of data because it's a thought process. It's something that we do in engineering and in programming is we think about how to solve problems. And the way that the problem was solved here was we took the total range of numbers and we split them in half. And then we ordered them from the smallest to the largest in both number sets, positive and negative. And a subset of that was, hey, cool. Remembering to flip the bits was a way to come up with the pattern. Let's check our math. Let's use the same thing that we used before. We're going to take a plus 7 plus negative 3. So this is 7, 0, 1, 1, 1. Now 3, what do we need to do? First, let's take a positive 3, which is 0, 0, 1, 1. And we need to flip the bits. Ready? So this is flipping the bits. Notice how the pattern just inverted. Well, you should be able to do that pretty easy, right? So a 0, 1, 1 becomes 1, 1, 0, 0. All right, that's one's complement. All right, so let's add now. Ready? 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1. And 1 plus 1 is 0, carry the 1. Oh, I end up with a carry bit again. There's that carry bit. Here is the rule in one's complement. Ready? If there's a carry bit, which we have a carry bit this time, then add it back into the pattern at the least significant bit. Okay, let's do that. Goes back here. Now let's add again. Ready? So I got 1 plus 1, that's 0, carry the 1. 1 plus 1, that's 0, carry the 1. I got 1 and 0. Now let's check our math. Are you ready? 7 plus negative 3 is equal to what? 4. Is that a 4 in binary? You better be shaking your head up and down. Yes. Success. We just validated. This works. Huh, okay. But we still have the 2 zeros problem. Oh. All right, so what do we do with that? Well, we need one more step. So we just proved the math works out brilliantly. That's great. So one's complement gets us almost all the way there. Now we got to deal with this double zero problem. So how can we convert negative 0 into positive 0? Okay. It seems really bizarre, I know. Why should you have a positive 0 and a negative 0? That just blows your mind, doesn't it? Well, you shouldn't. There should just be one absolute zero, period. Nil is nil, zero is zero. There shouldn't be two representations of it. So we've got to get rid of that. If I look at this pattern and I say that that negative one, I need to turn into a zero. How can I do that? What if I add 1 to that negative binary pattern? Well, let's just try this. You might not be able to see the pattern right now, so let's just walk through it and see what happens. All right, so here's my negative 0, 1, 1, 1, 1. I'm going to add 1 to it. So I go 1 plus 1 is 0, carry the 1. 1 plus 1 is 0. Right? Carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. Look at my pattern. 0, 0, 0, 0. Okay, cool. And I have a carry bit. Okay. Here's the rule in what's called 2's complement. This is 2's complement, by the way. Throw away the carry bit. Yep, that carryover bit just gets thrown away. So what we end up with is 0, 0, 0, 0. Ta-da! We just solved the problem. Let's take a look. So we go right back to it again, and we've seen this before. Let's look at, this is what we had before we solved the problem of 0. So let's go ahead, and now we need to add a 1 back into each of these. Here we go. Ready? That becomes 0. Yay! And then if I add a 1 to each of these, notice what happens. Basically, all I did was I shifted the entire pattern down 1 decimal. That's all I did. So I'm stuck now. I've got 1 extra decimal. What do I do with it? Let's go ahead and put it down here. Now I get a range of 1 more placeholder. Okay, so then my number system ranges from what? The positive are 0 to 7. The negatives are negative 8. Negative 8. See that? If that just blew your mind and you just aren't seeing it, I want you to back this up and listen to it again. You need to understand this, okay? So let's go ahead. Let's check our math again. Same thing. Are you getting bored with this 7 plus negative 3? Well, let's keep it going for consistency. So we're going to take that 7. Now we've got to convert the 3, right? So this is our positive 3. So how do we convert it? We got to go through 1's complement and then 2's complement. So 1's complement says to do what? Flip the bits. All right, so this is the bits all flipped. Then we need to add what? For 2's complement, we need to add a 1. So let's do that. And when we do that, what do we end up with? We get 1101. All right, let's go ahead and load that back in. There we go. So now let's do our addition. So we go 1 plus 1, 0, carry the 1. 1 plus 1, 0, carry the 1. 1 plus 1 plus 1, 1, carry the 1. That's 0. We get a carryover bit, right? There we go. And what did we say in complement 2? We can throw that away. So therefore, when I look at this, what do I get? 4. My math is correct. We just solved the problem. We now have a representation for negative numbers. And we do it through a complement 2 system. All right? Spend some time. Make sure you get it. You need to understand this. You really do. I mean, there are times when you need to deal with negative numbers, and it's going to help you to understand how negative numbers are actually represented in the computer. It becomes very important when you start dealing with instrumentation. You're going to say, okay, well, I don't deal with instrumentation. Well, you may at some point in your career. If you've got to pull in temperatures from a server room, or if there's some other system that is collecting information into a website, that maybe the website is being used to compute information that's coming from a digital system and pumping that information back out, whether it's instrumentation or something else. Being able to look at these numbers and understand these numbers is important to you. So our number system is pretty limited now, though, isn't it? we try to add numbers together. There are situations where we're going to get an overflow. So what about the overflow? Well, let me explain overflow to you first. All right. What happens when you add two numbers together and they're greater than the range of available numbers? So both of these numbers, a 7 and a 5, are both within range, right, of positive numbers because we go from 0 to 7 for positive numbers. So here's a 7, here's a 5. Let's add them together. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1, and that's 1. I don't have a carryover bit. And what does that equal? That would be 8 plus 4 plus 0. That's 12 in decimal. Oh, wait a minute. 12's out of range. You know why? Look at this. We go from 0 to 7 on the positive scale. 12 does not fit in there. We get an overflow in that case. And an overflow is going to cause an error. That's a good thing. I know if you say error, sometimes people go, well, we can't have an error. No, an error is a good thing. You want a computer system in any instrumentation that you deal with to have precise value to it. And what you want is if it does not fit the number set, it needs to cause an error. You don't want unexpected data ever out of a computer. You want expected data. So why do we discuss that overflow? Because the real world around us is infinite. Data is continuously flowing. Computers are finite. We've already discussed this. So we need a set of parameters to define expected behavior within this limited computer, this limited mechanical machine. If we tell it to add 7 plus 5 and there aren't enough numbers available to it, it better come back and tell us, nope, error. And that's what it's doing. So what are our takeaways? We learned about splitting the range of available binary bit patterns, right? We split it in half. We said that we had a total range of numbers and we needed to be able to deal with both positive and negative numbers. So we took the available information, the available data set, and we said split it in half. That's an important concept for you. You have to deal with the data that you're given and come up with creative ways of being able to manipulate data to fit the problem set that you have. This is the way that this was solved. Knowing that you have those possibilities available to you allows you to solve pretty complex problems. The lower half of the numbers were used for positive numbers. The upper half were used for the negative numbers. To compute the negative numbers, you flipped, right? You inverted the positive binary pattern and then you added 1. And an overflow can happen when negative numbers are outside the range. So a lot of important concepts happen through this particular topic, beyond just knowing that negative numbers can fit within a range. You need to understand what's available to you and how to get that mindset of problem solving. And that's what you had here in this particular topic.